Welcome everyone to the TCVS seminar series. This is the first seminar of the fall semester. And today we are hosting Chris Sugino from Stevens Institute of Technology. And he will give his talk on writing dispersion curves and breaking reciprocity with non-local acoustic metamaterials. Whenever you're ready, Chris, take it away.
Great, thanks, Gazan, for the introduction. Thanks, everybody, for logging in today on Friday. Happy Friday. So yeah, I'm going to talk about some of our recent work on this new area of research we're working on non-local acoustic metamaterials. I'll basically talk through two projects. I'll talk a little bit about metamaterials in general, and then I'll go through the kind of motivation for introducing these non-local interactions and why they're interesting. And then I'll kind of conclude with how we're actually building these things and testing them in experiments. So one quick introduction, since I know this is an open seminar. If you're not familiar with Stevens Institute of Technology, we're located in Hoboken, New Jersey, right across from Manhattan. So we're here. Manhattan's here. And since this is TCVS, I thought I would mention that ASME was founded at Stevens, right next to the building in which my lab is located. So ASME was founded in this building, EAS, and our lab is located right next door in Carnegie Laboratory. Of course, I'd like to acknowledge my group, who did pretty much all of this work that I'm showing. We're the Vibration and Acoustics Engineering Laboratory. My PhD student, Bilal, is the one who did most of this. I'm a new student, Jayi. And as well as a lot of really talented undergrads, Jasper, more recently Anastasia and George, and many others who I'll acknowledge as they come up. And yeah, we have two facilities. We have this kind of standard structural dynamics lab with a vibrometer, optical table, and we also have an anechoic chamber, which is really interesting piece of history in a lot of ways, but I'm hoping to sort of get it up and running again soon. So yeah, in my group, my kind of overarching question is basically how can we control and leverage the flow of mechanical energy, in the form of sound and vibration? So I always think about, ripples propagating through some medium, right? Something like this. So a lot of my work recently has been in kind of conventional structural dynamics, vibration, and metamaterials, so manipulating vibration with different architected structures, most commonly with smart materials, which I'll talk about later on. I also did some work in ultrasound, so I have a lot of interest in the applications of a lot of these metamaterial concepts in ultrasonic applications like biomedical ultrasound and NDE. Also have done some work on energy harvesting, not so much recently, but again, hoping to start that up again. And then more recently, obviously, maybe a lot of you are familiar with, there's a lot of recent interest in, how do we embed intelligence in structures? And that's kind of a new area for me and something that I won't have time to talk about today. So that's kind of my overall research goal. So to give a quick outline, so I'll briefly talk about what is a metamaterial. That's kind of the main thing I'll be talking about today. I'll talk about effective properties and dispersion relations in case you're not familiar, and then I'll start talking about this idea of a non-local metamaterial, define what that means, and talk about these two projects that we've been working on recently. The first one is basically to design a lattice that has an arbitrary dispersion relation, and the second is to realize non-reciprocity, so basically try to make a diode for mechanical vibrations. And then I'll conclude and talk about some future research directions. Okay, so again, my motivation is really manipulating sound and vibration, right? So I always think about it again like ripples in water, right? So given that kind of image in my mind, I think about how can we prevent or control that kind of propagation of energy, right, through that medium. So I kind of went through this thought experiment, right? There's only so many ways you can do this, right? So the first kind of obvious strategy is to put something in the water, like a large rock, right, that would block waves from propagating. And this is not desirable in a lot of cases, right, because that something that you add has to be very large generally, right? So it needs to be big enough to prevent that propagation. So in something like aerospace, that's not desirable. You could use a material which is more lossy, right? So if I used honey instead of water, that would prevent the propagation of energy. But obviously, I think the analogy is that, right, just like in structures, right, there's not many stiff materials that also exhibit good attenuation, right? So generally, that's not a kind of, at least not a straightforward option. You could try to absorb the energy, right? So you could do something like, add a vibration absorber, right? Add some other medium that's going to absorb that energy, that propagation. But generally speaking, this is not so useful because if I just add a few absorbers, right, the wave is kind of propagating everywhere, and ultimately that's not going to control that propagation, right, very effectively. The last one, which doesn't really apply in solids, is to add some sort of bias, right? Push the water away from you. If you add some sort of flow, right, to the medium, that would also prevent propagation towards you, for example. But that, again, is not really possible in a solid, although I'll talk about at the end how we can do that in a solid in a kind of indirect way. Okay, so the approach or the idea, right, behind a metamaterial is basically I want to invent a new material that somehow achieves my objectives, right? But again, I don't necessarily have a kind of natural material that would achieve those, right? So we're trying to design some equivalent material or some medium that exhibits the performance that we want, the properties that we want. Is the idea. Okay, so to do that, right, at least I'm not a material scientist, right? I don't know how to invent a new sort of, metal or alloy, right? We're really talking about something that's at a larger scale, right? So to do that, we have to talk about this idea, this relationship between, right, material properties and length scale, right? So essentially, my argument is that, right, the material properties that you care about, right, really depend on the length scale that you look, right? So if you look at an entire structure, right, you would be thinking about things like the average properties of that structure, right? The maybe average density, average stiffness, that sort of thing. As you kind of zoom in, you start to see individual parts, right? You see the geometry, you see maybe the fasteners on the structure, right? Those have different materials. And if you kept zooming in, right, you would see things like microstructure, or eventually the crystal structure, right, of the separate materials. Okay, so obviously the idea of material science is that we make changes down here at these low length scales, right, to make these new materials that we can then apply at these larger scales, right, to improve their performance. So the basic idea of a metamaterials, right, rather than work down here where it's very difficult to make changes, we instead add our own length scale, which is big enough that we can make changes at, right, and design different complicated structures, right, but at which is small enough that we can still have the kind of very large impact on the overall properties of our structure, right? So that is the kind of very high level idea of a metamaterial, right? We add this artificial length scale. We make a repeated unit cell, it's kind of like an artificial atom, right? We repeat it many times, and that gives us interesting effective properties that we couldn't necessarily have otherwise. Okay, so yeah, in acoustics or vibration, right, metamaterials have really received a lot of research attention. So I'm not going to talk too much about the kind of existing work, but there's a lot of work that's gone into this idea. So basically, a metamaterial is some architected structure that has a small scale repeated unit cell. So I imagine some sort of reasonable size structure, let's say, right? A scale at which I can make changes. So here are some, screws. I've, screwed this unit cell together using just regular screws and nuts, right? Where if I repeat that unit cell many times, right, I get a structure that has effective properties that are unusual. And by unusual, I really mean things like negative density, negative modulus, that sort of thing. So properties that would not naturally occur in a normal material. And people have basically shown to use, again, vibration as the focus, right? Basically that you can get any combination of positive and negative stiffness, right? And positive and negative density, right? So density and modulus, right? We can basically get all four quadrants where we have positive and negative or combinations thereof, right? And that's been pretty well established at this point, okay? So just to be clear, when I talk about metamaterials, I'm going to use dispersion relations quite a bit in this talk as a stand-in for their effective properties. So let me at least briefly define that. Okay, so when I talk about the properties of a material, I'm really talking about its dispersion relation. Okay, so a dispersion relation basically tells me how a wave would propagate through that structure, through that medium, through that metamaterial, right? So we're imagining kind of a plane wave, some kind of basic exponential, right? Like this, where we have a frequency omega and a wave number k, right? So it's basically spatial frequency. And for any medium, right, we have a set of dispersion curves that basically tell us how a wave at some frequency would propagate through that medium. Okay, so there's two things we get from here. We get the phase velocity of the wave. That's the velocity at which kind of an individual peak of a wave would propagate at that frequency. And we also get the group velocity, right, which is the slope, which basically tells me if I have a narrowband wave packet around that frequency, the velocity at which that overall wave packet would propagate. So the group velocity and the phase velocity are kind of the two things I get from here for free. Okay. And then basically because of the complex conjugate symmetry, I get basically two families of waves, right? The left propagating waves are in these kind of opposite quadrants here, and the right propagating waves are in the other two quadrants. Okay, so, and then, yeah, because these are basically complex conjugates of each other, these are always the same in a kind of a real structure. And there's one more thing that I'm going to talk about quite a bit. So again, I'm going to use these curves really as a stand-in for, how I'm changing the properties of a medium, right? So if I'm able to change the dispersion curves of my metamaterial, I'm basically changing how energy propagates through that structure. And if I can change that freely, right, that's really the kind of overall goal, right? I want to be able to change how energy propagates through that medium, right, through the introduction of band gaps and et cetera. Okay. So there's one more property here, which is this kind of left-right symmetry, and that is what we call reciprocity. So let me define that. Okay, so reciprocity is this property of a linear time invariant and passive medium, which says that basically if I have 2 points and I think about a sensor and an actuator, right, like an accelerometer and a shaker, right, at 2 points, A and B, right, I get the same signal if I change the sensor and actuator around. So again, using vibration as an example, right, if I have two structures with some two beams, right, I have a displacement on the left and a force on the right, I get some frequency response, right, the left displacement divided by the force on the right. This has to be the same if I flip my input and output around, right? So if I take instead the right frequency response function where I apply a force on the left and take the response on the right, these frequency responses have to be the same. That's the idea of reciprocity. And it doesn't matter what the structure looks like, if it's asymmetric, if it has loss, none of that changes this kind of fundamental fact, right? So it doesn't matter what I attach to the structure. In all of these cases, these two frequency response functions would be exactly the same. And that's because these are all linear time invariant and passive systems, right? No energy is being added to the system. They're linear, presumably, and time invariant, right? Nothing is changing. Okay, so those are concepts I'm going to talk about quite a bit. So I needed to define that, but I hope when I talk about the work that we're doing, this becomes a little bit more clear. Okay. So yeah, reciprocity can also be thought of as, again, in terms of dispersion, that basically my left and right propagating waves are the same, which means that I have this symmetry right about this k equals 0 line, right? My left waves and my right waves are the same. The dispersion curves are the same. Okay. Okay, so that is the idea of a metamaterial. So the motivation behind this work was really, trying to think about what are the limitations of metamaterials, because again, they kind of promised that we would be able to achieve properties that we couldn't otherwise achieve, right? And I think that's been pretty well established. So again, we have negative density, negative stiffness, all of that has become sort of normal now, which is really interesting. So if we think about the limitations of a metamaterial, right, the main thing that came to my mind was this idea that, metamaterials have unit cells which are basically local in nature. So I'm imagining now that I am this unit cell. Okay, so I'm some unit cell sitting in a structure. Okay, and I'm responding to some wave that's propagating through the structure, right? So here's my wave propagating at some frequency. Okay. So in a kind of typical metamaterial, right, my unit cell basically only reacts to the deformation that that unit cell experiences, right? Maybe its own deformation, maybe the immediate deformation, the deformation of the immediate neighbors, right? Those are the only things that unit cell senses, right? And that's therefore the only thing it can respond to, right? So schematically, what that looks like is this, right? As I'm going up and down, right? Maybe my restoring force is this arrow, right? It's proportional to my displacement, something like this. Okay. So if I take two waves at the same frequency, right? So these two waves are going up and down at the same frequency, right? My unit cell is going up and down at the same frequency. but different wave numbers, right? So a low wave number on the left and a high wave number on the right. Basically, you see that the responses are exactly the same, right? There's no dependence on wave number. The unit cell basically only sees the up and down motion at a certain frequency, right? So as a result, these two waves appear to be basically the same. So as a result, right, when we have these kind of local interactions, right, we only get frequency-dependent effective properties, right? I think of it as my unit cells can only distinguish between waves of different frequencies, which means my effective properties can only depend on frequency, right? I think that's pretty straightforward. Okay, one downside of this is that it makes it very challenging to break reciprocity, right? So you can use the same idea, right? Basically, my unit cell can't actually distinguish between a wave that's going left to right and right to left, right? This again will be exactly the same, right? This up and down motion is identical. So this makes it very challenging to break reciprocity, right? Again, I can't distinguish between a left or a right wave. As a result, it's not too surprising that, I can't change my behavior depending on direction, right? So it becomes very challenging to break reciprocity. You can do it, right, with nonlinearity or time-varying material properties, but it's I would say very challenging to do so. There's been a lot of work on this area. Again, I don't have time to cover in much detail. Okay. So this again has been pretty well established. You can get things like band gaps, right? These are quote unquote locally resonant band gaps, right, where we get a negative effective property over some frequency range, right? So again, this idea is that, right, when I do all this kind of local interaction, I get frequency-dependent properties. So in this case, this is the frequency-dependent stiffness, right, of my structure. And this has been pretty well explored. So the idea of a non-local metamaterial is if instead I imagine I had a unit cell, right? So again, I imagine I'm this green unit cell going up and down, but in this case, I have a sensor, this little red dot, positioned some distance away, right? Maybe it's another unit cell, right, that I'm responding to, for example, right? So I have a network of unit cells. Then I can get very different behavior, right? So in this case, I'm imagining, again, I have a sensor at some position, and I respond at this other location, right, where my unit cell is, right? So in this case, at a low wave number, I get this basically a little bit of delay, right? I'm almost still in phase with the input wave, just like before, right? A little bit delayed from that wave, right? But if I go to a higher wave number, right? So again, same frequency, but a higher wave number, my response, my unit cell response basically becomes completely in phase with the, excuse me, completely in phase with this incident wave, right? Basically, it's 180 degrees out of phase from what I showed previously, okay? So the basic idea is that, right, if I add this kind of non-local interaction, right, where I have a sensor some distance away, right, now I can change my behavior depending on wave number, right? So depending on this incident wave's spatial frequency, right, in addition to its kind of temporal frequency. Okay. So the nice thing about this is, first of all, it makes it simpler to break reciprocity, right? I think that's clear, right? If I basically distinguish between my response from the left versus my response from the right, that lets me add a directional bias. So this is kind of the equivalent to that like external flow that I talked about earlier, right? For a solid, basically I can react differently for a wave coming from the left versus from the right. And I'll talk about that a little bit later. Okay. So yeah, this idea of a non-local metamaterial, basically we take a metamaterial and we imagine that we have unit cells that interact kind of at a distance, right? So some distance away. And that gives me this wave number dependence properties, right? So this is basically a new design parameter I can use, right? I can, in addition to varying how my properties depend on frequency, I can also change how they depend on wave number, spatial frequency. Okay, and this gives me additional design freedom. Okay, that's the kind of overall idea, and I'll try to show that through these two projects. Okay, so first I'm going to talk about how we can use non-local interactions to get basically any dispersion relation. So this is some work we're currently working on. It's almost published, so it should be published soon. And yeah, this is kind of a logical extension of, if I have a metamaterial, I can get basically increased design freedom. If you add this additional design freedom using non-local interactions, you can get basically any set of properties, any set of dispersion curves. So a logical next question is, given that that is true, how do I actually build something with non-local interactions? And I'll talk about that in kind of the second part. Basically, we use piezoelectric transducers and shunt circuits, which are non-local, right, to approximate this kind of, ideal non-local sensor actuator response. So in the first part, I'm going to talk a lot about a very generic kind of basically a toy model of masses that are interacting via some set of forces. Okay, so we imagine I have some unit cell with some degrees of freedom in this vector x, right? They have some mass m, and they are experiencing some forces which depend on the unit cell at a distance delta away, right? So this F delta is basically the force acting at a distance of delta, right? So if it's zero, that's kind of the conventional local interactions, but for any non-zero delta, that's a non-local interaction, right? A force that's generated at a distance, okay, or in response to a distant deformation. So we can do Bloch's theorem, right? Get the dispersion relation of this thing, and basically you get a kind of standard MCK eigenvalue problem. The only difference is that my M, C, and K depend on wave number mu. Okay, so mu here is my kind of dimensionless wave number. And the interesting thing is that those effective properties, right, M, C, and K, are basically Fourier series expansions, right, over my forces or my interactions, right? So for example, my effective mass is the static mass matrix plus this kind of Fourier series where these M deltas are kind of my inertial interactions at a distance of delta, okay? Same thing for K and C, right? I can basically say there are these Fourier series where each term in the Fourier series is an interaction at that corresponding distance, okay? So this was kind of the original thing that we saw, and we said, okay, this probably means in principle, right, if I can change these three properties, right, M, C, and K, as a function of wave number, I should be able to specify the roots of this equation, omega, right, as a function of wave number, right? And that would be basically specifying my dispersions to be whatever I want, in theory. That was the idea. Okay, obviously, it's not so simple in practice because this is an inverse eigenvalue problem, right? So I'll talk a little bit about that and how we solved this problem, okay? But that was kind of the idea, and this is why we got excited about these kind of non-local interactions. Is basically, right, in principle, you can specify these things to be anything you want, right? Again, as a Fourier series, right? So I can, in principle, get any properties I want. Okay, so in this first part, I'll talk about, this inverse design method that we developed for getting an arbitrary set of dispersion curves, okay? And the idea is that we wanted to try to use that design inverse method, right, to identify, basically what dispersion relations are actually possible under certain conditions, right? So if I have a set of properties that I want, are they actually realizable in a kind of simple way, or are they kind of impractical, right? And then, in the last part, I'll mention basically ways that we are going to try to realize these non-local interactions, right? I think that's almost as important as this, right? I can show that I can do this, but how do I actually build something that exhibits those properties? And again, let me acknowledge Bilal, who's the one who did pretty much all of this initial work. All right, so the first thing I'll say is that in 1 degree of freedom, right? So if I have a 1 degree of freedom system where, instead of a set of coordinates, I just have a single displacement. So I'm imagining basically a chain of masses, right? Identical masses. There's a nice closed form expression if you take some 2 dispersion curves, right? So for a 1 degree of freedom system, I have 2 dispersion curves, omega 1 and omega 2. I can take those curves and get the closed form expressions for my damping and stiffness interactions at some distance of delta. Okay, so this is kind of the, it's a simple argument. Basically, I'm doing an inverse Fourier series, right? I'm getting the coefficients of my Fourier series based on the coefficients of my characteristic equation, right? So this is exact, right? It's not an approximation anymore. And we can show we get basically perfect agreement, right? If I specify some curves for my dispersion curves, I can get basically perfect agreement between my desired and my calculated dispersion curves. So in this case, for example, we got some non-reciprocity, right? We made a wave going faster in one direction than the other direction, right? So my right propagating wave is very fast, my left one is very slow, okay, in this example. Okay, so that is relatively straightforward. It becomes basically incredibly more difficult once you look at multi-degree of freedom unit cells, right? So once I start specifying more than 2 dispersion curves, I'm specifying 4, 6, 8, right, dispersion curves. This procedure becomes much more challenging. There's basically no way to solve it analytically, right? I think intuitively, right, this is a problem with multiple solutions, right? It's basically, again, I can find any number of matrices that have the same eigenvalues, right? Again, all I'm giving my design eigenvalues of these matrices, right? So there's going to be multiple solutions. So we came up with basically a numerical way of calculating these interactions, right? So we basically, first we truncate our Fourier series. So instead of allowing infinitely many of these interactions, we truncate it at some distance n delta, right? So I'm only going to allow interactions up to a certain distance away. These are going to be my unknowns, right? All of these interactions, my static mass, maybe my MC and K at a distance of delta, right? Those are my unknowns. I solve for my kind of corresponding dispersion, right? For these kind of approximate interactions, right? I discretize my wave number. I assign, calculate the total error, right? So I basically integrate my dispersion curves to get the total error under those curves. And then I have to do this assignment. So this is kind of the tricky part, right? I need to find the assignment between my calculated dispersion curves and the desired ones that give me the least error. Okay. And then once I have that, I have the error, right? So this is just an optimization routine. I have can basically varying my interactions to try to minimize the error between my calculated and my desired dispersion curves, right? And we can add constraints, right? We can add inequality constraints and equality constraints, right? Inequality constraints for things like I want my stiffnesses to be positive, and equality constraints for things like I want my lattice to obey Newton's third law, for example. So yeah, we apply constraints to basically constrain the lattice that we get out of all of this math, right? So we, for example, can base it just on the characteristics of the dispersion curves we want, the effective properties we want, right? If those properties are passive, basically reciprocal in the real and imaginary parts, right? We can basically say, okay, I would have this kind of behavior where I have basically normal springs and dampers, which are obeying Newton's third law, right? So the constraints are here and they're relatively straightforward, right? Obviously, depending on the specific type of dispersion, this can get a little bit more complicated. So like if you have a non-reciprocal real part, you can use what's called PD symmetric damping. Things like this are really change the type of solution that you get. So it's really important to do this. And even if we constrain everything as much as we can, we tend to still get multiple solutions when we do this inversion. So I'll highlight that at least in the first case study. And so basically this works surprisingly well, as I'll show. Even though it's just a numerical method, this I think expanding things with non-local interactions is kind of the correct approach to this, and it works really well. I'll just mention there's one kind of quirk of using these kind of discrete mass spring damper models, basically, when you have non-local interactions. So there's kind of an ambiguity about your unit cell, right? So normally when we think of a unit cell, right, I think it's pretty clear what that is. It's the repeated unit, right, of your lattice, let's say, right, in a metamaterial. Okay, but in a non-local system, you can kind of shift things around, right? So here's an example of a unit cell that's kind of not well chosen, right? So I've chosen two masses here with the kind of corresponding interactions shown by these arrows. Right, so the thing that we do to kind of simplify that is we form a long chain, we connect it end to end, so we make a little kind of ring of unit cells, and we position that according to some algorithm. We basically use like a graph plotting algorithm to place these in a kind of logical way, and that basically lets us find the unit cell that's the simplest or the kind of closest interacting unit cell, and lets us kind of simplify the interactions down. So in this case, for example, here I have an interaction at a distance of 3. But once I simplify my unit cell, it actually only has a distance of 1, right? So it's actually it's just nearest neighbor interactions, right? It's just that when I chose these two masses in this case, right, they weren't really the correct ones to choose, right? There was a better selection of masses, right? Here it's Mn and Mn minus 2, right, for example. Okay. This is kind of a quirk, and I think it's interesting, but for the most part, it doesn't really change the inversion, right? We get the same lattice. It's just that the unit cell is kind of corrected after the fact. We don't do this while we solve because it's quite computationally intense. All right, so let me show some case studies. So here's an example where we started with a lattice, which is this 4 degree of freedom lattice that's proportionally damped. So it has springs, which are shown by these lines, and dampers, which are shown by these lines in this second plot. And these little circles are my degrees of freedom, basically. This is, one-dimensional, so, imagining basically like out-of-plane motion if you want to think about what this would physically represent. So out-of-plane vibration in this case. So the dispersion relation of this system is here. It's pretty normal. It's reciprocal and passive. So I get, some damping. So I have an imaginary part and a real part to my frequencies. And there's 4 curves, right? 4 dispersion bands that I need to solve for. 4 unique ones, right? There's also 4 that are negative, but they're identical. So if I invert this while fixing the mass to be the same, basically the same masses on each of these degrees of freedom, and don't really apply any other constraints, right? This is the sort of lattice that I get. You can see that it's totally different. So my stiffness and my damping are kind of totally different than the original one. But the dispersion relation agrees almost perfectly, right? So this is the red curve is the inverted dispersion, again, compared to the kind of dashed line, which is the target. So we can basically get a family of these lattices that have the same dispersion relation. So here, for example, if I let the mass vary, so now these kind of larger masses have larger circles have larger masses in my lattice. Again, I get a totally different realization where, again, my error is basically 0, right? I'm basically getting perfect agreement to my target dispersion. And then the interesting thing is that as a test, right, we basically said, okay, what if I tell the solver that I want to find a solution which is proportionally damped? Right, so if let's say, for example, I was going to build this, it would be desirable to have something where my damping kind of has the same structure as my stiffness, right? Because I get damping where I have connections. And in that case, we basically recover the original lattice, right? So I think there's some interesting kind of design possibilities here, right? We can, again, kind of get a lattice which realizes the dispersion that matches what our requirements are. And in this case, yeah, we were able to recover that kind of original input lattice. Okay, so this gave us some confidence that this would work. So the next thing we wanted to try was to give it a dispersion relation where we knew that it would fail, right? So to do that, we basically took a locally resonant lattice. So this is the lattice here. It has kind of a base chain of these red masses connected to these resonant masses up here. And we chose a very large resonant mass. I think it's 10 times the base mass. And this gives us a very wide locally resonant band gap in this example. Okay, so in that case, right, we said, okay, what if I constrain my mass to be smaller and try to get the same very wide band gap? It should be impossible, right? Regardless of what else I do, that should be impossible. And that is true, right? So if I constrain my masses to be the same instead of this one being 10 times this one, I allow all the non-local springs that I want, kind of connect any masses that you want together, you still can't do better than this kind of mass limited bandwidth, right? So I'm still kind of limited in the total bandwidth that I can get, right? And this is because of that limited mass. So the interesting thing is that you can actually replicate the dispersion with limited mass, but only if you add this kind of PD-symmetric damping, conservative PD-symmetric damping. In this case, where basically in addition to stiffness, I have this kind of plus and minus coupling through the damping matrix. You can think of this as gyroscopic coupling or something similar to piezoelectric coupling, depending on what field you work in. Okay, but essentially, if I'm able to exchange energy right between my kind of resonator masses and my base lattice, right, then I can replicate that effective added mass. And this kind of matches my intuition from piezoelectric systems, right? I can, using a piezo, right, replicate the effective mass as long as I have enough energy exchange, right? So, in practice, this would be a kind of very well coupled piezoelectric system. But again, I think it's just interesting that, again, this damping interaction lets us replicate that kind of effective mass of this very large addition. Okay. So yeah, this basically indicated to us that if I allow this kind of energy exchange, right, or energy input through the damping matrix, then I should be able to get pretty much any dispersion relation. Okay, so the next thing we tried was a much more complicated dispersion relation. So we gave it this kind of discontinuous set of dispersion curves. They're reciprocal, but obviously they have these very large discontinuities, right? Either in the slope or in the slope and the value, right? And we thought, okay, can I realize this using this numerical method? And we can pretty well. So here's the damping matrix or damping lattice, if you want to think about it that way. Again, it's PD symmetric, so really each of these lines represents a plus and a minus interaction. And our stiffness is this kind of interesting, basically, we have one uncoupled chain of masses and then 2 very well coupled masses. And again, they all exchange energy through the kind of damping matrix. So we get relatively good agreement. And we see this kind of typical like Fourier series kind of ringing, right? Where we don't get perfect agreement at these jumps, but we get this kind of oscillation that's similar to the Gibbs phenomenon, right? So yeah, we can't build a lattice that has these infinite slope points, but we can kind of approximate it as well as we would like. Okay. So the next thing I'll show is basically how we can simplify this down, right? So again, if we're ever going to build this, this would probably be impossible. I'm pretty confident in saying that, right? So we want to find a simpler way to get the same sort of dispersion. So what we did is we did this kind of regularization. So we applied this L1 regularization or lasso regularization where we penalize this L1 norm of our interactions. So instead of minimizing just error, we minimize some lambda, which is our regularization parameter, times the L1 norm of our interactions. So as we increase lambda, basically we get simpler lattices. And that trade-off is shown here on the left as I increase lambda. So at 0, I get this inversion I showed previously. As we increase it, we get simpler and simpler lattices down to a much simpler one, right, for a relatively large value of lambda. The downside of that, of course, is that the dispersion gets less close to the target, right? So in yellow is the original one. In blue is this kind of intermediate value, which we call kind of the optimal point, which still agrees very well, but obviously is still simplified. And then red is what happens if we really, quote unquote, over-regularize the system, right, and take a larger value of lambda. We get a much worse agreement to the input dispersion, but again, a much, much simpler lattice that would realize it. Okay, so this is basically our design tool to try to, identify where are you kind of willing to stop? What level of complexity are you willing to accept, right, if you're going to build something like this? So this is a really nice tool for that simplification. And yeah, I'll go through this relatively quickly, but we also looked at some time domain simulations. Again, we can give it pretty much anything we want. So here we gave it this very non-reciprocal, very, again, abrupt sort of dispersion. And we validated that we got exactly what we wanted in the time domain. Just leave that there. And then the last thing we did, and this was mostly as a little bit not serious, but I wondered if we could write text using dispersion curves, and that's what I put in the title. And it turns out we can do this a little bit. So here's an example where we wrote SIT for Stevens Institute of Technology. We had to add this one band here just to make it a real lattice, but otherwise we can pretty much do this. I mean, obviously limited by the number of curves, basically increases the computational cost, right, of doing this, but for the most part, we can do this. And this is the lattice that does this. It's fairly complicated, obviously. So all that's to say that we can basically generate these lattices that give us any dispersion relation we want at this point, right? So again, using these non-local interactions, we can essentially realize any dispersion relation, okay? So that's great. But probably the logical question, and hopefully you're all thinking this is okay, this lattice is kind of ridiculous, right? Okay, maybe the stiffness part you could implement through some very complicated geometry, but the PD symmetric damping part is kind of ridiculous and not physical, and that's probably true, right? It would be very complicated to build, right, out of some mechanical components. Okay. So the next thing I want to talk about is basically how do we build something that has non-locality in it, right? And that is a really tricky open question in my mind. Okay, so if you think about a mechanical force, right, something that's pushing on something else, right, those are always local, right? It's not like we don't have like Jedi, right, in our structures, right? We can't apply force at a distance typically, right? So it's quite challenging to do this. Okay, so there's one approach which is to basically use some combination of stiff and soft elements, right? So if I combine stiff elements and soft elements in a clever way, I can basically emulate a non-local connection, right? If something is stiff, you can see that it acts kind of quickly, right? And that force may act non-locally kind of at the same time scale as my soft connections, right? Which might be the local ones. So this has been done experimentally. So this is a very nice paper looking at roton dispersion, but basically they came up with this geometry that achieves this kind of third nearest neighbor interaction using these kind of diagonal elements. and this kind of rigid frame on the outside. But this basically achieves that objective. And again, this is kind of an approximation, right? Ultimately, I would still describe this as a local system, right? It's just that you can get away with some clever design elements, right? If I design my lattice correctly. Okay. So what I'm going to talk about in the rest of the time that I have is instead of doing this, right, to take it a little bit more literally, and basically take a sensor and an actuator and do feedback, right, non-collocated feedback to get this kind of non-local interaction, right? So I'm going to measure something at a unit cell, some distance delta away, and apply a stimulus at a unit cell, a different unit cell, right? And that gets me that non-local interaction. It's a little bit different. It's not exactly what we want, but I would say it's close, and it's really a nice approach to implementing this without having to rely on this kind of complicated geometry. Okay. So yeah, I'll talk about this work we've been doing with non-local piezoelectric metamaterials. So again, as a way to implement a non-local interaction, that's really a true non-local interaction, right? It's instantaneous, basically much faster, right, than the speed a wave propagates through the structure, right? This feedback can be very quick, and we can tune it with external circuitry. And we published this recently if you're interested to find out more. Okay, so yeah, we're interested in these non-local systems. Again, basically, how we can implement non-local interactions using piezos and shunt circuits. And in this case, actually, we're really focused on breaking reciprocity. So I'll talk about that in a second. How can we use these non-local interactions to, like I mentioned earlier, right, add this directional bias to our structure, okay, and then experimentally validate. And again, Bilal worked on this a lot. I'll also acknowledge Jasper, who meticulously bonded piezos to the structure I'm going to show. Not the one that I'm going to show, but the next one that we made. So I'd also like to acknowledge him for doing that. Okay, so the system I'm looking at is this. It's a piezoelectric beam with these circuits connected. I don't have time to go through the detail. All I'll say is that my analogous term to my non-local forces is this non-local current in this sum here. So instead of forces, I have currents. Instead of displacements, I have basically electrical fluxes, but otherwise it's quite analogous to the same thing that I showed previously. And we have kind of bending vibration of the piezoelectric structure. So if I look at the dispersion relation of that system, it's a nice kind of simple expression. We have three parts. We have the electrical curves. Those are the curves of my electrical lattice. So again, thinking of my fluxes and currents as kind of analogous to my masses and springs from earlier, right? These are my two electrical dispersion curves. That is coupled to my elastic dispersion. This is just a parabolic kind of Euler-Bernoulli beam shape through some piezoelectric coupling alpha, right? So through the piezoelectric effect. Okay. So the kind of interesting thing is this is not quite what I wanted in that I can make these two electrical dispersion curves anything I want using non-local connections. But it's not like I'm directly modifying the dispersion. Instead, I'm modifying how these two curves interact with my elastic dispersion. So I'll show that in a second. It's not quite analogous, but it's getting to where we want it to be. So here, for example, this is what I have. So in this case, I have my elastic dispersion, this kind of parabolic shapes. And I'm hybridizing that with some electrical dispersion. So here I'm showing just the locally resonant case as an example. Right, so if I couple those curves together, I get these blue curves, and those are kind of my overall dispersion curves for my piezoelectric structure. Okay. So the nice thing is that I can actually make those curves anything I want. So, in that case, I was showing just a constant. That was the locally resonant case, right? But I can actually make those dispersion curves anything I want. So if I only want to hybridize, let's say, for left propagating waves, right, I could use a dispersion relation like this. It's kind of sinusoidal shape. Instead of using a straight line, I'm going to make an electrical lattice that has this dispersion curve. And in that case, I get hybridization only in certain directions, right? And this would let me get non-reciprocity in the overall system in principle. Okay, that was the idea we had. So we were thinking about, how do I build a electrical lattice that only has one-way propagation? That's what's required for that. And it's not too complicated. We basically have a typical resistor, a local resistor, plus a non-local VCCS, voltage-controlled current source. So I have a current that's generated at a unit cell n. It's related to the voltage at a distance of n minus delta. So a distance of delta away. And if I do that, I get this kind of sinusoidal shape like I wanted, right? Again, I hybridize that with my elastic curve, this kind of parabolic shape. And I get these two types of non-reciprocity. Shown here, I can either get a gap, this is what we call type 1 on the left, or I can get this kind of veering, which is what we call type 2 on the right. And yeah, the nice thing is that in this model, we can show that there's basically two types of non-reciprocity that arise in these structures. Basically, we either get a gap. So this is a plot of that non-reciprocity versus the number of unit cells. I'll just highlight two different sets of frequency response functions, right? So if I take n equals 34 unit cells, I can show that I get this really strong non-reciprocity at this specific frequency. It's this kind of point here on my plot on the left, where basically my right propagating waves have an anti-resonance, but my left propagating waves do not. This corresponds, let me just mention really quickly, this corresponds to this kind of hybridization on the right, okay, this kind of theory. Okay. And yeah, if I increase the number of unit cells, I can also see that kind of non-reciprocal band gap right on the other side. And each of these have a kind of distinct shape. Not go too much longer. So, if I have this, we call it destructive interference. Basically, it's two waves in the same direction interfering with each other, right? So if I have this kind of two slightly dissimilar frequencies, I get a beat envelope. So we see that beat envelope here, right? That kind of cancellation of two slightly different waves, right, gives me this kind of cosine, roughly cosine shape envelope. To the right, but to the left, I get propagation. In the case of a band gap, right, so in the case of this kind of typical band gap, I get exponential decay. That's this bottom left figure, and that's pretty normal. Whereas if I look at this other destructive interference point, we get this, again, this kind of sinusoidal envelope, again, showing that kind of spatial beat. And this is a nice way to distinguish between these two types of mechanisms. The really interesting thing, and this was not expected, is that destructive interference, so this kind of cosine cancellation, is much more efficient than the band gap. So, I mean, a lot of people in this field look at band gaps a lot. It turns out that this kind of destructive interference is a little bit more efficient if you just want non-reciprocity, right? If you just want these waves to cancel in one direction, not the other, it kind of makes sense, right? We have this kind of cosine decay instead of an exponential decay. So it can be a lot more efficient to do this, and that was not something we expected. Okay. So let me just show the experiment. So we have this beam. Again, Bilal made this first one. We made another one, which is not shown here, but Jasper made the second one. The second one is really good. The first one was pretty good, but the second one was amazing. We have this piezoelectric beam. It has 57 unit cells, so 114 piezos bonded to it. And we implement these shunt circuits in printed circuit boards. I strongly recommend you do that if you work with piezos as much as you can. Once you get past like a few unit cells, it's really worthwhile to build all these circuits in PCBs. So we built these PCBs that have, again, that resistor plus non-local VCCS. And we got really good agreement between the model and the experiment. So the kind of results are summarized in this figure on the left. So this is a plot of our non-reciprocity. So in a passive system, it has to be 1, right? It has to be unity. This ratio of basically left to right responses. And the dashed line is the model, and then the solid line is our experiments. For kind of two different circuit configurations. So we can basically change the frequency at which the non-reciprocity occurs by changing the spacing in the circuit. So this is a distance of 3, this is a distance of 2. It changes the frequency at which we get hybridization, right? And that basically changes the where that non-reciprocity occurs. And we also got really good agreement between the FRFs, right? The individual FRFs, and also the deformation shapes. I don't have time to talk about it, but really good agreement between the theory and experiment, really regardless of the parameters we used. And just to highlight, we got a maximum contrast and maximum non-reciprocity of 17.4 decibels, slightly less than an order of magnitude, almost 10 times, basically 9 point something times at steady state. So I like to say that we basically made a kind of vibration diode, right? Where if I hit the structure from one side, I get basically nothing out on the other. But if I hit it from the other side, right, I get basically full transmission to the left. Again, this kind of shape, right? This this one is the best one, right? If I hit it on the right, I get basically full transmission. If I hit it on the left, I get this really strong attenuation on the other side. Again, just using these non-local shunt circuits. Okay, yeah, just like this. More recently, this summer, we really pushed the envelope and we tried to increase that non-reciprocity as much as possible. And this hopefully will be written up and published soon, but we got up to 62 times non-reciprocity. So I think there's a lot of promise here to use this. The system is large, but I think we can make it smaller in the future. And we got this really broad bandwidth of non-reciprocity as well, which I think is really interesting. So not just the maximum amplitude, but this the bandwidth, right, of that non-reciprocity is really, really large. So I think this is a really, exciting area, and really, we're thinking about ways to use this now, right? So I think we're pretty confident now that this works. So we're thinking about ways to change the setup, right, optimize it further. And yeah, this I think is what anyway, if you're at SPIE next year, this is I'll be talking more about that this work at that conference. So we're thinking about how do I build kind of full non-reciprocal circuit analogs, right? So diodes are kind of one of the fundamental elements of electrical circuits, right? So we're imagining how do I use that for elastic components? I think critically these non-reciprocal devices are linear and time invariant, right? Which I think makes them much simpler to use. They are active, which is important, right? Otherwise they couldn't be non-reciprocal, but they are active. But it's all kind of analog circuits, right? Relatively simple. We could make them much smaller if we had an electrical engineer, for example. But yeah, we're really interested in how we can apply these to make basically customized sensors, right? You can imagine basically separating transmitter and receiver, right, in a NDE application and things like that. So yeah, we're interested in all of that. Happy to talk more about that if you're interested. So yeah, just to summarize, we are working a lot with these non-local interactions, and I hope I convinced you that they're interesting and useful and that they let you get any dispersion relation that you want. Albeit with complicated perhaps impossible to build, but anyway, potentially realizable long-range interactions, right? Again, I need these really distant connections to get this design freedom. Okay, we can use regularization to simplify things, and this is really important, I think, if we're going to actually build these things. We can use piezoelectric systems to implement non-locality, right? Again, this kind of circuit to vibration or system analog, right, basically shows that they're equivalent. And we can use this to basically break reciprocity for, I think much better than previously. I don't have a kind of comprehensive analysis of the literature, but I'm pretty sure 62 times is probably the strongest non-reciprocity someone has measured in vibration, at least. Okay. So I'll just acknowledge NSF and thank you for sticking through the talk and happy to take any questions.
Thank you, Chris, for the great presentation. Do we have any questions for our speaker? You can unmute yourself and just go ahead.
Hi, Chris, this is Pai here. Thanks for the excellent presentation.
Hey, Pai.
I have a question on slide 26 where you compare the passive system with your system, and you said something that I didn't really understand. You said something
You said 26, this one?
Oh,
different one.
29, sorry.
29, okay.
Yeah.
Yeah.
Yeah. So I guess the question is that when you talk about your system, you said something like it's a little bit different, not exactly what you want. I don't quite understand why you said that. This is exactly what you want, right? This can do anything you want.
Right. I mean, so the real difference is this thing. Basically, like, I would love it if I could directly change this part of the dispersion, right? Like, I would love to change just the kind of basic elastic backbone of the dispersion relation directly.
Uh-huh.
Right? But instead, I change these curves to be whatever I want, and then I have to hybridize them. right? So it's not like I can directly modify this part of it, if that makes sense.
Okay.
You know, it's maybe a subtle distinction, but I would love it if I could make a material that has any, just elastic, right? Just, here's my dispersion curve and I get it, right, through these non-local connections.
Uh-huh.
Instead, this part is fixed or relatively fixed. I can make this part, again, anything I want. And then they hybridize together, right? So it's not like a full kind of design freedom, if that makes sense. I'm still limited by the underlying elastic dispersion a little bit.
Okay. Okay.
That makes sense.
Thank
Yeah.
you.
That's
Yeah.
the main difference. Yeah.
Cool. Thanks a lot.
Mhm.
Any other questions?
Yeah, Chris,
Mhm. Hey, Dan.
going back to your inverse procedure, which you did numerically with optimization, and you said you can get any set of dispersion curves. So inverse problems have an existence property, right? So it's
Mhm.
what guarantees that you can get any dispersion curve? Because
Yeah, I would
there's
say
no
we didn't. That's a good question. Yeah, we didn't really prove it, if that makes sense.
right,
So, like, we had this idea. I mean, it's based on this, basically, right? It's based on
right.
this idea that, right,
So
if I,
you can. I tried doing something quite a bit simpler than what you did, which is very
Mhm.
cool, by the way. I like it. That for a very simple spring mass uh, lattice system, um, and solved an inverse problem, and I could solve it, and I could prove existence, not uniqueness, but didn't need uniqueness. But I couldn't get a physical system back. Everything
Mhm.
I got was non-physical.
Mhm.
So are you running into that in terms of constructing these?
Yeah, I mean, I would say, yeah, like maybe this is the example, right? Like, and this is why we were doing this study, right? We gave it a dispersion relation, which we knew is kind of difficult, or at least, this kind of wide band gap, which,
Right.
should not be possible. And we tried to achieve it in a non, you know, we thought maybe, okay, maybe I can get this band gap just by using all these non-local springs. And that turns out to be not possible, right? In this case. Um, so yeah, we kind of get the sense, and we haven't proved it yet, that right, if you allow this energy exchange, like if you allow this kind of PD symmetric damping, even if it's conservative for a reciprocal system, that you can pretty much get anything, but we haven't proved anything like that, if that's what you're
Fair
getting.
enough. Thanks.
Yeah, I mean, it seems like it works, um, but we're not mathematicians ultimately, but
And of course, you haven't found one that didn't work, right?
right, exactly. Yeah.
It looks like Alex
Chris?
wants to ask a question.
Yeah, hi, Dan. Hi, everyone. Chris, I was intrigued by one of your statements in your presentation. I
Mhm.
think it went like this. So the damping matrix couples the modes. Is this what you said?
Maybe at some point. Yeah,
Yeah.
or
No. I like it. No,
Mhm.
it's very nice because I think the role of damping has generally been underestimated in vibration engineering. So, in what sense, could you please repeat in what sense you are using non-proportional damping, non-classically damped systems
Right.
to
Yeah.
do this coupling?
Yeah, basically, you can, I mean, so this kind of comes from physics nowadays. People are really interested in this thing called PT symmetry. PT symmetry is in a vibration context basically means that the damping matrix has, let me just pull up the equation.
Do you need closely spaced modes?
No, it's nothing like that. I mean, basically, it just means that the damping matrix has a certain symmetry, like the interaction from the right is negative transpose the interaction from the left. That's kind of the, um,
And how to achieve this?
I mean, if you were going to achieve it, yeah, that's a separate question. I mean, you would need some complicated sensors, actuators, right? I mean,
So
I think,
basically, we're talking with active, right? Actively.
yeah, it would, like, especially in the case of a
Okay.
non-reciprocal real system, it
Okay.
would have to be active.
Because I was going to say,
Yeah.
if you have a system, and sorry for taking, for prolonging this, If you have a system with closely spaced modes, which is passive, right? No classical damping will couple these modes, and you might even introduce kind of very interesting waves so it's something to consider perhaps. Of course, this will not break reciprocity. You will need to break, yes, you need to break passivity, but yeah. Okay, thank you.
Yeah.
I was just intrigued by your statement.
Yeah, thanks.
Any other questions for Chris? All right. Thank you all very much for joining us today for the TCVS seminar. We have another seminar in November and December. So we'll be in touch with announcements in the upcoming weeks. Please join us for those as well. Thank you, Chris, for today's talk. It was amazing.